Okay, yeah, well, thank you, Chris, and thank you all for coming, and thanks to the club for the invitation. It's really, it's great to be here, and also really interesting to learn about this organization. It's funny, I'm from originally from southern New England. I grew up on Cape Cod, and then promptly kind of ran away from home up to Maine after I got out of high school. But I've been kind of driving back and forth past this bay all my life. So really great to be making a stop here, and just really interesting to hear about the Pelagic Club and organization, and just what a great idea. So I'm very excited to meet you all and to learn more from you about what you're doing. So as Chris said, I'm a professional mariner. I'm a licensed captain and have spent most of my career working at sea in the maritime industry, primarily on tall ships, on sail training ships, and oceanographic research vessels. But it's a fairly salty crowd, right? So that may mean more than it does to the average crowd. But just to note that to be a professional mariner, like there's all sorts of stuff you can find yourself doing in the maritime industry. And actually now, I spent most of 30 years going to sea, and now I've been going to sea part-time and have a full-time job at Maine Maritime Academy, training people for the maritime industry. And there's another MMA down the road here as well, so probably some of you are familiar with that. But I always like to, just for sort of, standard talks, I like to put this little number down on the bottom of the first slide and ask people if they can guess what that means, okay? I'll just jump ahead and with the reveal, right? That's the average number of tonnage of shipping that transits the world's oceans now every year, right? In the contemporary ocean, about 11 billion tons of shipping at sea. This image is taken from a site called marinetraffic.com, which probably many of you may be familiar with, right? It just allows you to see the AIS and transponder signals of all the vessels that are at sea and transmitting at any given instant. And it looks like you could throw your boat away and just walk across the ocean on the ships. It's not really like that, but just kind of testament to just how much traffic there is out there and how many different kinds. People tend to think of seafaring. It's a very traditional, very historic occupation. But there's actually, more ships, more cargo, more people at sea, more people employed in the maritime industry now than at any point ever before in history. So I think a lot of what I'm going to talk about tonight kind of involves history, but that's always, I feel like, it's a good place to start things. If you have kids and are looking for a way to send them out into a gainful occupation, I want them to launch with their own independent source of incomes. There's never been a better time to join the maritime industry. It's incredible. Students are graduating from the maritime academies and going right out into, I won't even say what they're making now in their first year out of school. So it's a tremendous, tremendous period of growth and innovation in the industry, which is also really great. So this book, Breaking No, Reading the Glass, okay, is a book that I wrote, starting with disclaimers, right? I never really thought of myself as, as an author, and I'm certainly not a meteorologist by trade, but I wound up writing this book about weather. And it just kind of grew out of, well, several things, a long-term interest in weather, right? As mariners, right, we're all sort of end users of weather. Also just in the seagoing environment, right, which I think, all of you are familiar with to one degree or another. That like, the ocean and being at sea, it's like one of the ultimate sort of on-the-job learning environments, right? And so in the industry, there's a tremendous amount of teaching and training goes on at sea. So you spend a lot of time sort of thinking through explanations of things, both for yourself and the people you're working with. Mariners, it's really the only workplace I've ever been in, but I can say it's probably like this in many industries, but mariners by and large are tremendous teachers and explainers and thinkers, right? And so I just felt like, just over time thinking about weather, and like I said, sort of putting together explanations for myself and other people, I began to write chapters for classes I was teaching, things like that, and just sort of writing stuff down for myself. And, a couple of people suggested, well, hey, this might be a book. And people that I began to talk to about in the publishing industry, they were very interested in sort of the maritime. What's the maritime world like? People want to know. And it's like, well, everybody I know is on ships, so I don't think anybody really wants to know about it. And they said, well, actually, most of the world doesn't spend their life at sea. So the storytelling element of being at sea, and then also one of the significant challenges, I spent a lot of time on research ships working with scientists, one of the main challenges of science is not just discovering the facts, gathering the data and discovering the facts, but telling the story, right? Telling the story in a coherent way so that people kind of at the non-scientist level, the non-expert level, can become literate in the topic, right? So, you know, I've always loved books that do this for all kinds of topics, right? You know, there's always been my favorite authors, the ones who could take a book. I mean, whoever thought you could sit down and read an 80,000 word book about oranges, right? But there is one, right? A great book. So I kind of thought, well, what if there could be a book like that about weather? Maybe some of you have read it and can say whether or not I achieved that objective. I was reading before I came to speak. I was reading Chris's description of my talk, and it kind of looked like basically in a paragraph form, he got the whole book into a paragraph, and so that was what I was gonna talk about. I will touch on some of that. What I'd like to do tonight is talk about a few topics that I address in the book, kind of just to give you a sense of the way that I approach a few different subjects, and then. You know, as I said a minute ago, this is a very salty crowd. So if you feel like, you know, this is all stuff that you already know, please ask questions, or, you know, if you just want to ring the bell and just, you know, regress to C stories, we can do that also. But starting off with a definition of what is weather. Okay. And this is the best sort of single sentence definition of weather I've ever run across. Do any of you know Finn Perry? Is anybody this is the kind of person that somebody in the room might know? He's from Massachusetts, I think west of Route 24 somewhere. I don't remember the town, but a career. Somebody there know him? Sounds like yes. A very accomplished cruising sailor, and accomplished in a number. He's written a bunch for Wooden Boat, and just done all kinds of stuff. But he came up with this explanation of weather is simply the first law of thermodynamics influenced by the Coriolis effect. And I thought, wow. What a thing. Okay. Unfortunately, I had already written the book by then. Okay. So all I can do is tip my hat to Finn whenever I get the chance. So what I want to talk about tonight, like I said, I'll run through just sort of a quick discussion of just the fundamentals of weather. Like I say, if this is all stuff that you all already know, you can stop me and I'll move on. I'd like to talk about global winds and how that's influenced the history of just human populations moving around the world, because I think that's a really effective demonstration of, like, you know, where the people are has a lot to do with, you know, where the winds blow in a global sense, right? How they got there and what they chose to do, and sort of how populations got distributed around the world. And then kind of inevitably, like a lot of our conversations about weather now involve climate and climate change. And to, again, you know, with the disclaimer that I'm not a climatologist, you know, talk about some of the stuff that, you know, marine navigators are thinking about in the context of a warming planet. So to start with, right, stuff that I like to be sure of and that I sort of lay out at the beginning of the book, you know, weather, right, it happens up in the sky, but it's actually happening in a very, very, very thin layer of the atmosphere called the troposphere, which is actually kind of like the lower 10 miles of the atmosphere. And it depends on several different measurements of the atmosphere, but, you know, you could say it was about 100 miles thick or so. But weather really happens down in the troposphere, kind of down below 50,000 feet, roughly. That's where 90% of the mass, so that's where 90% of the material of the atmosphere is, all the water vapor and nearly all the air. So that's where weather happens. And then, you know, another great quote describing this environment, right, the fuzz on the tennis ball. Okay. And I say this to college students, and nobody knows who Sally Ride was, but I think probably some of us remember her, right? You know, tremendous characterization of the atmosphere seen from space. So what I'm going to do now is I'll run you through the just meteorology in a nutshell. I take about a semester to teach this to Maine Maritime Academy students, but I think you guys are all probably much smarter, so we can get this done in a few slides, right? Weather is just about different areas of temperature and density in the atmosphere, and the atmosphere basically trying to equalize itself, because different parts of the atmosphere are warmer and colder. Colder air is less dense, okay, and tends to sink, dense just means more mass per volume, so tends to be heavier, if you will. Sinks under the influence of gravity, and as it does so at the surface, right, that leads to rising pressure, okay, rising surface pressures. And then warmer air doesn't rise spontaneously, but what happens is air is warmer, cold air sinks around it, sort of forces it aloft. And when that happens, we get lower pressure at the surface. And kind of the final step to keep in mind in this case is that as air gets lifted, it tends to cool off through the process of lifting. As it does so, the water vapor that's there all the time condenses. It turns into clouds. So clouds are, well, they're clouds, right, of water droplets and ice crystals that form when air gets lifted and cools, and the water vapor turns back into a liquid or solid state. Condensation also releases heat into the atmosphere, which is a pretty important thing when we start thinking about like how storms develop and build energy and propagate themselves. Sort of more on that to come. So the only piece I left out of that, this is kind of another version of the same diagram right off the NOAA website, okay, and sort of showing the same thing in a schematic way. We have an area of warmer air rising off the surface, leaving lower pressure at the surface, and then we have cooler air that's sinking, settling towards the surface and leading to higher pressure. And the general flow, nature abhors a vacuum, right? So the general flow is from high to low. And then interestingly, this is actually a cyclical process. So, as air rises, okay, in areas of low pressure, it actually rises and travels and then sinks somewhere else, right? So it can't just rise or fall indefinitely. So really, anyway, you have areas of high and low pressure near each other, what you're really looking at is some kind of a cyclical system of air circulation that's going on. So, again, a little bit more on that.
The moderator.
The one piece we haven't talked about yet is this thing called the Coriolis effect. Okay,
the moderator
that doesn't have anything to do with the way your toilet flushes, but is a motion. It's apparent motion that's influenced by the fact that the Earth is a rotating frame of reference. So as wind flows, for example, towards high pressure in the towards low pressure in the northern hemisphere, it tends to be deflected to circulating around a low pressure system. The northern hemisphere, okay, is going to circulate in a counterclockwise direction, so-called cyclonic direction. Air around a high pressure system, kind of opposite, right? So in a room full of sailors, I understand this is
it was almost 90 degrees today.
Anyway.
20-degree spread across the city. So as far as what's happening, you see that little area right there? Those are actually little raindrops that are falling from the cloud. So dry.
The flow of air from high to low pressure, okay, we also call that wind. And we have a system of notation that we use on weather maps. This is today's weather map of the North Atlantic. I always tell students, when I look for the stuff that's easy to find, you're trying to figure out where you are. And Newfoundland is pretty easy to identify. There's England, Ireland, okay. You can see that, in addition to all these sort of colored lines, there are just all these sort of wavy lines on the map, okay? And these are isobars, right? These are lines of equal pressure. Just as though this were a topographical map, the places where the lines are spaced more closely just indicate a steeper gradient of pressure. So you're looking for a narrower spacing of lines, and that's where you see
almost an inch of rain, and then travel to the north. Once you get north of Plymouth, not much. Boston, 1/100th inch of rain. Fitchburg got a few rain.
Hey, whoever's on the
winds come from, okay? It comes from the fact that the Earth itself, okay, is not equally heated by solar radiation. In fact, and again, we're all sort of comfortable with this intuitively, right? But the poles, the higher latitudes are cold in general, and the middle latitudes, and particularly the tropics, are a lot warmer. That has to do with a couple of reasons. One is that you sort of think of a beam, a column of solar radiation as being kind of like the beam of a flashlight. Where it meets the sphere of the planet, it's spread out over a larger area. So if you think about the beam as just being sort of a circular column of sunlight meeting the surface of the planet, it meets the planet at more of a right angle in the tropics. Okay, so the number of photons per area at the surface is much, much greater in the tropics, and the poles kind of get a short shrift in terms of the amount of solar radiation they get. That's on an average day, right? But there's this other thing going on that leads to a change in sort of difference in solar radiation, right, in different parts of the Earth. We have these things called the seasons. Funny, we should be talking about this right at the autumnal equinox, okay? But twice a year, the hemispheres, both hemispheres of the Earth, get equal hours of daylight and sunlight. But as you move into sort of winter or summer, okay, we can see over here summer, summer solstice, so midsummer in the northern hemisphere. The Earth's axial tilt, the fact that it's tilted over at about 23.5 degrees as it orbits the sun, is going to mean that for part of the year, the northern hemisphere is going to get more radiation from the sun, while the polar southern hemisphere is almost completely dark. In fact, the Antarctic is without sunlight for parts of the year, as is the Arctic, right, during the winter. So again, thinking about like what drives global weather, understanding, the poles are much, much colder, right, where we've got, the air is much denser. And in the tropics, the air is perennially warmer. So what we're looking at here is a cross section of the atmosphere, just sort of taken between the equator, 0 degrees latitude, and the North Pole. And just to start off with this sort of tilting surface, what this diagram, it's what I like to call a cartoon, right? It's, sort of an enlarged look at the atmosphere, sort of idealized. But this is the troposphere, okay? This is the active part of the atmosphere in terms of weather. And we can see, first of all, the atmosphere is a whole lot less dense near the equator. It's much warmer and less dense. And as we get towards the poles, kind of in a series of steps, it gets progressively more dense. So in the equator, in the tropical regions, you get air that's pretty much continuously getting lifted off the surface because it's the warmest, wettest air on the planet. So it's the least dense, okay? So it's sort of being continuously displaced by cooler air, making its way sort of south or, down from higher latitudes and towards the tropics. At the poles, okay, we have air pretty continuously sinking, right? This is the coldest, densest air on the planet. But in the middle latitudes, we've got something kind of interesting going on, okay? And this is, happens to be right where we are. Well, Maine and Massachusetts, right? Very close, kind of roughly halfway between the equator and the pole. And our weather here, okay, is dominated by sort of the interaction between warmer air making its way kind of up from the middle latitudes and cold polar air. So this is what's called the polar front, okay, at the surface. Not a term that you hear a lot, but it's pretty expressive because it just describes, right, the sort of middle latitudes, kind of between, just north of the tropics to about 40 or 45 degrees north. The air is generally warm, and the higher latitudes, the air is, consistently very cold and dense and much drier. And the weather we get here is really driven by the interaction between that warmer, warmer middle latitude air and the cold polar air. So we get a flow sort of towards the tropics. That air is sort of lifted up away from the tropics, gradually cools off and sinks kind of around 30 degrees north, these areas that we associate with sort of continuous high pressure, right? Bermuda, San Diego, the Sahara Desert, right? Those are all around 30 degrees north. That air sinks and a lot of it makes its way towards the poles, sort of flows north in the northern hemisphere and meets up with cold polar air. So that's why, the weather we get here is pretty much a continuous back and forth between, warm, moist air and cold, dry air. So we take this whole diagram, right, and sort of spread it out in a polar sense, right? This leads us to what we think of, as sailors, right, as kind of the global wind patterns, right? So if you think about in the tropics, right, I think probably many of you have been fortunate enough to sail in the tropics. Where is the wind from, nearly all the time? East, mostly east, right? You're in the trade winds, right? So that's air that's flowing towards the tropics and gradually being deflected by the Coriolis effect very consistently, right? So much so that, the palm trees all lean in the same direction and the rain always happens on one side of the island, et cetera. And then in our latitudes, okay, our wind is sort of pretty consistently westerly most of the time. Okay, so it's interesting to be saying that on a weekend when they're talking about easterly winds, but for the most part, most of our wind is like, southwest, northwest, right? Again, not news to most of you, I suspect, interrupted by occasional easterlies. So look at some pictures of that, right? Sailing in the tropics, right? It's a great place to sail, particularly if you want to sail west, okay? With the wind always out of the east. Getting upwind in the tropics can be a little bit of a challenge in a sailing vessel, particularly one that looks like this. Okay, but here we are in our latitudes, our native latitudes, and we're looking at an example of a satellite, satellite eye view of what I was talking about a minute ago. We're looking at just sort of standard, this is a, meteorologist term, but a baroclinic cyclone. So this is a low pressure system. It's just like one of our North Atlantic garden variety low pressure systems. It develops develops from the interaction between cold polar air and sort of warm air from the mid latitudes. The cold polar air sinks, okay, and it displaces that warm air upwards. Warm air is lifted up, it cools off gradually, and releases moisture as clouds, okay. This is an area of low pressure, so air is generally converging towards the center. So the overall pattern of wind around this system is going to be counterclockwise, a so-called cyclonic pattern of rotation. These systems, baroclinic just means differences in temperature. Okay, so the best way to describe a baroclinic cyclone, right? What we have here most of the time, tropical cyclones, like if you think about what's the difference between just sort of your average temperate, low pressure system and a hurricane or a tropical cyclone. Tropical cyclones are all made up of the same air. That's all tropical air. So they get all of their energy from the lifting and condensing of moisture in warm air. So there are no temperature differences really in a tropical cyclone, where, these sorts of extratropical cyclones that we deal with here all the time, right? How does this all go, right? We live around here. This happens, once, twice, sometimes 3 times a week in the wintertime, fall and spring, sometimes in the summer, right? You get wind out of the southwest. It's kind of warm, and then maybe it gets wet and windy. And then at some point, right, you get a wind shift. The wind shifts from the south to the north, and then what happens with your wind shift? Wind shift to the northwest, and yeah, it gets cooler, it clears off, right? So that's your cold front, so it's just a transition between the two air masses. So, populations over time have taken advantage of these sort of global weather trends to get around. And it's interesting. I like looking back at this because you understand really, how sophisticated the understanding was, I think, of these weather patterns for a long way back into time, depending on where you look. We'll look at the Atlantic first. We'll look at the Norse, who are, as far as anybody can tell, the first Europeans to get to North America, and then the Spanish and the Portuguese, the Southern Europeans. We'll look at the navigators of the Indian Ocean, okay, who relied pretty much on the system of monsoon winds, a full knowledge of the system of the monsoon winds to get back and forth between Africa and sort of South Asia and India. And then also we'll look at the Pacific navigators. The Polynesians are sort of the standard bearers of that, but I have the asterisks there because they're actually just one. They're sort of the most storied of several island voyaging societies that spread themselves across huge parts of the Pacific before anybody else was there. So, Lanso Meadows, northern tip of Newfoundland. Has anybody been here? It's a fascinating place to go. Newfoundland's a fantastic place to travel. There's all kinds of stuff there. You can pretty much have the place to yourself. But right at the northern tip of the Great Northern Peninsula in Newfoundland is the only verified Norse or Viking, if you will, settlement that's been located in North America. It's pretty clear that they probably went elsewhere, but this is a settlement. It was identified in the 60s by a couple named Anne and Helga Ingstad, archaeologists from Norway. And by studying written records, the so-called Norse sagas, right, they collected enough geographical information that they were able to trace their way to this particular spot, did some digging, and were able to figure out that for about 100 years anyway, there was a town there, okay? And there were people there long enough to build structures and set up an iron smelting forge, and actually go back and forth between some of the other Norse ports in the North Atlantic, Greenland, Iceland, and they were able to get back, and this became part of the written record. So this wasn't just one lucky bunch who sailed off and disappeared and camped in Newfoundland and until they vanished, right? This was sort of an ongoing settlement, like I say, for about a century. And they got there in ships that looked like this, okay? They didn't have color photography, so we've had to look for a more recent example. This is a ship called the Dragon Harald Hafag. It's a replica of a Viking longship that was built about 10 years ago in Norway, and actually did a transatlantic crossing that summer. So visited North America, retraced some of these routes. And as you can see, it's about 30 meters, 35 meters, so a little over 100 feet long. Very, very rugged, fast, probably wet and uncomfortable, but very seaworthy with one big square sail, 25 pairs of oars. So, a very fast boat, but probably not a boat that was well built to sail to windward. Okay. And so that, kind of indicates that the Norse had a pretty good understanding of how non-tropical cyclones worked. And they understood that if you were trying to get from, Norway, what's now Norway anyway, to what's now Newfoundland, right? You want it to be kind of up in the northern part of the ocean basin where you could take advantage of the easterly winds, the so-called polar easterlies, kind of that are on the northern edge of these North Atlantic cyclones. And then when it came time to get home, right, they understood that, from there they needed to sail south, or at least get far enough south that they could get into the influence of these westerlies, okay? And like I said, there was repeatability here, and they, there was pretty active sailing back and forth to Iceland and Greenland. And then, at least for about 100 years, there were trips, and this is New England under the clouds here, but I think the star is, right about where we are now. So several hundred years later, this is Columbus's first voyage. So we're looking at, 1492, right, a date that was all drilled into our heads long ago. But Columbus was one of a series of Southern European navigators who made voyages. Columbus, as we know, made voyages to North America, kind of thinking he was going to India. But in any case, the way that he did this, he sailed, being in southern Spain, Portugal, kind of already in the northern rim of the tropics, fairly close to the trade winds. It was pretty well understood that you could get south, and actually the first place that Southern European navigators got to were the Canary Islands. The trade winds are sort of northeasterly, and they kind of bend around to the east. And it was pretty well recognized that you could sail south and west just about as far as you wanted to go. But the crux discovery here was this thing called the Volta do Mar, which is just this, well, you can sail west as long as you want, but how do you get home, okay? And sort of what preceded Columbus's voyage is a series of shorter voyages that were undertaken by other sailors within that culture. And they figured out that you could sail west in the trade winds, and then if you turn north and were patient, you could eventually find your way up into the westerlies, okay, and get back to Europe. And that's been credited with, that's as far as anybody can tell, is how the Azores were discovered. And it was a good sized island chain. The Azores are actually kind of distinct in that there was no pre-European population there as far as anybody can tell. Canary Islands and the Cape Verde Islands were already settled by the time the Spanish and Portuguese got there. But the discovery of the Azores was really the first test of this Volta do Mar. You can go west, but you got to turn north if you want to get home. And Columbus effectively did a giant-sized version of this. He sailed west in the trades to, in fact, right, the Bahamas and Cuba, Hispaniola, and then back to Spain and Portugal. Contemporaries of Columbus, right? So he was trying to get, the money here. This thing that everybody was trying to do is to establish a sailing route to the East Indies, right, to the Spice Islands, because there were various reasons that it was politically and geographically difficult to go over land. So kind of contemporaneously with Columbus, there were some other navigators. There was Bartholomew Diaz and successfully Vasco da Gama, 1498, were eventually able to sail around the Cape of Africa and up into the Indian Ocean and actually reach the East Indies. And sort of the way they did this, and again, the crux that they, sort of the risk that they took, the bet that they made successfully was that this sort of system of trade winds and westerlies was mirrored in each of the ocean basins. Okay, we know that now, right? It's just a fact. But think about, sort of a leap of faith that really was, right? To say, okay, well, it works this way in the North Atlantic, but in this great unknown South Atlantic, if we sail south, eventually we'll get into westerlies. So that was kind of sort of the splitting of the atom, right? Was to realize that pretty much any ocean basin was going to have some kind of a reciprocal weather pattern. The other thing that the Europeans had to do to get to India was to solve the monsoon. And the Indian Ocean has kind of its own, this whole sort of, Indian Ocean region, and the western South Pacific is heavily under the influence of this system called a monsoon. Monsoon's kind of a general term, right? Arizona has monsoons also. So, but the largest monsoon system in the world is in the Indian Ocean. And a monsoon is really just like a giant version of a sea breeze. Like, you know, if you're used to sailing in Buzzards Bay or something like that, you get up a nice August morning, everything's calm, right? Nice, calm, peaceful morning. And then sometime by like 1:30, 2 o'clock in the afternoon, it's honking, right? That, you know, southwesterly is blowing right up the bay. You know, that's kind of what the monsoon is like, except it's a seasonal wind and it's driven by where you have a large landmass that heats up and cools off sort of alternatingly in summer and winter. So the Indian Ocean monsoon occurs as, you know, Asia heats up, the Asian landmass heats up and drives a sea breeze off the Indian Ocean. So you get this warm, wet wind off the Indian Ocean, southwesterly, really, well, just like Buzzards Bay, right, in the summertime. And then in the wintertime, you got the monsoon reverses itself. So in the wintertime, you know, the land is much, much colder than the water. So you get air sinking, cold air sinking over Asia and blowing back out from the northeast across the Indian Ocean. So there's kind of an annual reversal. And you could see very, very easy to get from Africa to India with the wind out of the southwest. With the wind out of the northeast, right, in one of those old-timey Spanish caravels or whatever you're in, not so much, right? So it was the understanding of these cycles, and I think, you know, obtaining the knowledge from the locals in whatever way they obtained it, right, that was really the crux of, you know, the settlement of India. You know, the Portuguese were in India until like 1962. Or something I ran across, actually, when I was working on the book, the settlement of Goa, right? The Indians finally booted the Portuguese out, but it was in our lifetimes, right? And it was actually a war between Portugal and India in the early 1960s that nobody seems to know about. What's also interesting, this is an example of a, what you might call it a dhow, right? Which is one local term for these types of, you know, very large lateen rigged sailing craft. This carrying cargo under sail in the Indian Ocean lasted, interestingly enough, until right around the same time it lasted in our part of the world, kind of mid-20th century. There was still a lot of cargo being carried commercially under sail. And, you know, also interestingly, there's still people there that are, you know, that are preserving the sailing culture. So this is a picture from Wooden Boat Magazine. It was taken in 2020 by somebody who got over there and go sailing with some of these people. So just like you can, you know, you go to Maine or, you know, there are various parts of New England, right, and find schooners operating. Similarly, right, in the Indian Ocean, there's still operations. By now, you probably go on a windjammer cruise, right, on a vessel that looks like that. Okay, so now the Pacific. Okay, and if you look at the, you know, if you look at a map of the Pacific, right, and you look at it, what do you really see? The first time you look at a map of the Pacific, mostly just water, right? There's not much there to see but water. And then you get really close, right? You look and there's all these little dots, right? And you realize that there's actually all those little tiny dots. I mean, if it's world map scale, you really got to look to see them and read the fine print. But, you know, all those little dots are island chains. And by the time the Europeans got to India, in fact, well before that, all those islands were populated, right? They all had settlements on them, in some cases very significant settlements, and sort of an active system of commerce travel back and forth between these islands. And it's been proven, you know, archaeologically, there were no written records, but, you know, archaeologically demonstrated these populations moved back and forth, gradually migrated across the tropical Pacific, making their way out of Southeastern Asia, and then just made their way east across the Pacific. Hawaii and New Zealand were about, Aotearoa, the Polynesian name for New Zealand, were sort of the last two major island masses to be settled. Okay, Hawaii about 1200 AD and New Zealand at around the same time. But Tahiti, where in the pre-European time, they figured there was as many as 1 million people, okay, 1,000 years ago, more, okay, 1,000 years ago, Tahiti was settled, and Rapa Nui, also known as Easter Island, right, was settled at about the same time as Hawaii and New Zealand. And it's possible, right, there's some signs that, in fact, you know, these voyages, some of these voyages, things like, you know, plants and things like that that have been identified that, you know, seem to be South American plants that are found in some South Pacific islands. There's some reasonable evidence that some of these voyages got all the way to South America. So amazing, right? And this demonstrates, you know, kind of on a really grand, like a planetary scale, that these people, these cultures understood how to sail. They understood the wind patterns. And one of the most impressive things to me, right, is I look at this map and, you know, pretty easy to sail north and south, right? Anybody can do that. But, you know, they're moving mostly from west to east. We're here in the tropics. Where's the wind mostly blowing from in the tropics? It's out of the east, right? So they made their way upwind in sailing canoes, okay? And so to do that, right, the wind doesn't blow out of the east all the time in the tropics, just most of the time, right? So periodically the patterns are interrupted by, you know, you get your tropical cyclones, right? You have your El Nino years, things like that. So, you know, they not only had the craft, right, and the navigational knowledge, which is, you know, somebody else's lecture, but I think they understood enough about like seasonal and interannual variations in the wind that they could take advantage of those, right, and recognize chances to sail against what would have been the prevailing winds in any particular year. So, you know, commercial sail, right, you know, carrying large cargoes at sea kind of lasted into the early 20th century. There's this thing that we think of as the Clipper route, which was, you know, basically carrying bulk cargoes from, you know, primarily from places like South Australia and some from South Africa, things like wheat and nitrates and things like that, cargoes that weren't real time dependent with small margins. These were carried in sailing ships, and they took advantage of the fact that if you're down here in the higher latitudes of the southern hemisphere, well, two things: there's very little land to get in your way, and, you know, as a consequence of that, the wind blows like crazy nearly all the time, right? So there's a belt of very, very strong westerly winds. You can sail very fast, okay, as long as you feel like going east, not west, okay? And then they would peel off and go, you know, back and forth up to Europe, right? So they would sail south and then east, and then just continue, instead of turning around, they would just continue their passage east around with the prevailing winds behind them. You know, this is not a clipper ship, right? But these are the routes that have been, you know, that have been used, that are in use today, right? Because there's various high performance around the world sailing races, right? You know, single-handed and multi-handed, right? But, you know, very fast vessels built for this purpose. They don't carry any cargo. The interesting thing is a lot of the records that were set by the clipper ships, you know, many of them have fallen, but only recently, right? So there's some amazing passages taken by some of the last vessels carrying cargo under sail. This is kind of a lead into the last thing I want to talk about, which is climate. You know, one of the things that sort of the last, sort of the final, we'll call the final sort of age of commercial sail, sort of overlapping the 19th century. It was by that point, you know, meteorology had really had begun developing as a science. And one of the things that came out of that era was this tool called the pilot chart, right? Which is just, it's kind of like the farmer's almanac, right? It's an accumulation of climatological data. So if you're planning a sailing passage, an ocean sailing passage, and, you know, I'm sure some of you have done so, right? One of your tools is you can say, okay, well, you know, I'm getting underway in September in the North Atlantic. What can I expect, you know, for prevailing conditions based on a, you know, long multi-year average in terms of wind direction and, you know, locations of the ocean currents and frequency of tropical cyclones and how far icebergs are likely to come to the south, things like that. That's all printed on these pilot charts. There's one for every month of the year. This began again in sort of the first half of the 19th century at the behest of somebody named Matthew Fontaine Maury, who was a naval officer who was one of the founding officers of the U.S. Naval Observatory. You know, so the Navy was kind of, in that point, getting into the business of hydrography, right? Really of oceanography and cartography, and recognizing that weather really was a science. So like I say, you can still get these. In fact, you can print them off from the, you know, the government, the NGA, right? The, you know, government scientific data agency, or one or several. You can get the stuff online and print them for free. The problem, okay, is that these are all based on, kind of like your farmer's almanac, right? These are all based on old baselines of climatological assumptions, right? That were fairly consistent up until fairly recently. Okay, and sort of I'll hold that thought. I've just got one more slide here before we start talking about climate, but this is just again, talking about recently, right? Looking at the last 30 years, right? This is us, okay? This is all of us going on sailing passages. And you can see like pretty consistently, right? The blue dots are going west, the green dots are going east, okay? And you can trace that out pretty much, going west in the tropics, going east in the middle latitudes. Not too many people in the Southern Ocean anymore, a few, okay? And then north-south is red, red and yellow, okay? And you can also use this map to identify, Hawaii must be right there, right? And there's Bermuda, obviously.
I'm confused. Why are these patterns existing when ships go every which way they want to?
These are all sailing vessels.
Oh, sailing.
Yeah, these are all sailing vessels, right? Thank you for asking. Yeah, these are all reports. This is probably from things like Inmarsat C and things like that. Satellite communications gear. So these are all sailing yachts. Exactly. Yep. Yep. So right, 1990 was right around the time that we could all, afford to buy something, that used satellites and was actually small enough to bring with us on a sailing vessel. So things are changing, okay? And this is a map from the Climate Change Institute at the University of Maine, where I went to graduate school for a couple of years, but I'm not a climatologist. But this map is relatively easy to interpret. And what it's showing is basically it's a comparison between planetary temperatures, sort of an average 20-year period, roughly 20 years, the last 20 years, right? 2005 to 2021. Yeah, I know that's not 20 years, but ish, right? Okay. And then an equal period of equal length preceding that, right? So 1979 to 2004. And what the coloration just indicates is the changes in temperature from the average over the preceding 20 years, okay? And, red on these maps means warmer, okay? So on average, right, if we look up and red means warmer, the first thing you notice is that, well, it's very hard to find anything. Blue means colder, and it's very hard to find anything that's blue, except way down here in the Southern Ocean. But in particular, the poles, the higher latitudes are the warmest or the most warmer, right, over the last 20 years. Somewhere between, if we come down here to the scale, these are Celsius, right? So these are the big degrees, right? So, somewhere around 5 degrees, so that we could say like the polar regions are 5 degrees warmer in the last 20 years than they were in the 20 years before that. So that's a significant change, right? And so that's been enough, that's one of the things that's driving the sort of observable changes in climate that we've seen. And there's all sorts of ramifications, right, which we're just sort of beginning to get a handle on. But from a navigational standpoint, right, as a mariner, you sort of get asked, well, how does this affect sailors? And the first thing it does is, like all these old tools, things like pilot charts, which are compiled with old data, may still be useful, but there's a certain buyer beware characteristic to them. Things like the assumptions that we make for the advent of hurricane season, or the extent of trade winds, sort of where we'll find certain atmospheric features that we're used to finding at specific times or location, right? Some of those assumptions aren't as durable as they used to be. But here's some actual data, right? The last 15 years, we just saw, they're the warmest in recorded history. And actually this afternoon, I was just sitting in a traffic jam on Route 93, honestly, listening to the radio and hearing about how 2024 was the warmest year on record so far. What was the last warmest year on record? 2023, okay? So most of that extra heat is absorbed by the oceans, okay? Water is a much more effective thermal or absorber of thermal energy than land. So there's a huge amount of that extra heat has been stored in the oceans. That's led to a significant change in sort of average sea surface temperature. And this looks like a really small number, but so it's a 0.8 degrees Celsius. Okay, so that's about 1 Fahrenheit degree, little more than 1 Fahrenheit degree increase in the last 100 years. Okay, and that's, I don't know, to me that never really sounds like very much. But climate scientists use all kinds of incredible comparisons to show you how much energy this is. It's like millions of nuclear weapons worth of energy, okay, to raise the temperature that small amount. Yeah.
The plot you had up there before, you talk about the poles warming, but the South Pole looked as though it didn't warm hardly at all. And the whole warming was at the north, or we just got looking as far south as.
Well, you can see, right, so we don't see the full, this doesn't go all the way to, well, I guess it goes to 90 south. You can see, I mean, it's warmer here. We see some regions, right, and there's actually a lot of melting that's going on the polar ice shelf, the Antarctic ice shelf, right? So there's some areas of concentrated, warming here along, but definitely the Arctic is warming faster than the Antarctic, which they're not fully clear on why. Although one thing that's happening here is you can see the Southern Ocean at the surface. These temperatures are actually cooling. That's actually because the winds have increased, and that's stirring. It's actually just something called upwelling, which sort of stirring of cold water up from the deeper ocean. So the wind activity is actually, at least temporarily, driving colder air at the ocean surface. These are like the screaming 50s, yeah, right. The screaming 60s, the furious 50s. Well, we don't have a circumpolar ocean really up north, or at least where we didn't used to, or maybe about to, right? But yeah. Is there a question?
Yeah, do you know of any theories that explain why the North Pole is moving up at such a rate, much more than everything else?
Yeah, it has to do with I think the major influence has to do with the fact that as things warm up, the sea ice decreases, so there are less and less areas for smaller and smaller parts of the year that are covered with ice. Okay, and at that point, typically you have ice. Ice reflects nearly all the radiation that hits it. Right, ice sort of acts like a mirror, whereas an open ocean is very, very efficient at absorbing energy. So things warm up, the ice melts, there's more exposed ocean, which is then able to absorb more heat, more ice melts. So it becomes, scientists like to call it positive feedback thing, where just things warm, and what happens, the result of the warming encourages further warming.
Are these for air temperatures, like at 20-foot elevation, or what?
I'm not sure. Yeah, I'm not exactly sure where the measuring point for this. These are surface temperatures, right? These are not ocean temperatures. So tremendous amount of heat, and there's a couple of great teams actually. Well, in Massachusetts, in fact, locally working on this stuff. There's a tremendous scientist at MIT named Carrie Emanuel, who's part of the team that spent a lot of time working on connections between global warming and tropical cyclone activity, I've been to a couple of his talks and read some of his papers, and his point that he makes is that over this interval of time, there's been about the warmer oceans and the warmer atmosphere means it's about a 6% increase in the amount of water vapor that's in the atmosphere over the oceans. And I was reading about the big rainstorm they had in North Carolina just a couple of days ago, and I ran across this acronym that I actually hadn't heard before, but it was the same thing, WAP, okay? And WAP is water available for precipitation. So it's the amount of water vapor that basically the amount of rain that the atmosphere can make in any location. And that's gone up by 6% over this measurement time. And the other thing that Carrie Emanuel is saying is that, because of that, right, just as far as the thermodynamics, right, the actual math, that means if you're looking at a tropical cyclone, there's been about an average, like a 25 knot, increase in the potential energy that these storms can reach, right? So if before, they were kind of limited to 155 knots, right, as though that wasn't enough, they're now able to, reach, as much as 25% beyond that. And there's also in Massachusetts, right down in Woods Hole at the Woods Hole Research Institute, there's a scientist named Jennifer Francis. She was at Rutgers prior to that. And she spent a lot of time working outside of the tropics, looking particularly at things like the jet stream, which is the sort of upper boundary between the cold polar air and the middle latitude air. And as that boundary gets less pronounced, right, the poles are getting warmer, the jet stream gets weaker, okay? So the sort of climate boundaries that we're used to seeing, again, aren't as robust as they were 100 years ago. So we're probably running short on time, but I've just got a couple examples of that. So this is the 2020 hurricane season. Okay, that was a record hurricane season in terms of the number of storms. 30 named storms. 2021 wasn't any slouch either, right? So this is 28 named storms, okay? And if we start looking at sort of record tropical cyclone years, this is 2022, okay? Sanibel, Florida, Hurricane Ian, a Category 4 storm on landfall. So these are all the, well, 9 of the last record tropical cyclone years. And what we can see is that all but 2 of them fall within the last 30-year period, and all but 3 of them are clustered since the year 2000, right? So we have 1995, which is a record year. That was eclipsed by 2020, but now it's kind of, as we look down, we can see just all of these record cyclone seasons, 1933, 1887, and you're kind of getting back to the earliest part of record keeping. But it's sort of in the modern era of record keeping, 7 out of the 9 record tropical cyclone years in the North Atlantic have been in the last 3 decades. This is from the National Hurricane Center, as is this. And this just shows, they're looking at the most powerful storms. So these are the Category 4 and 5 hurricanes. And since 2000, so 2000 to 2020, which is the last year that I have data for, this graphic has data for, basically the average number of Category 4 or 5 hurricanes. So these are hurricanes above 135 knots, okay, has essentially doubled, right, from year 2000, right? This is a 20-year running average from about, 1.2 to like, say, 2.2, okay, in 2020, okay? So pretty much twice as likely in a 20-year period. Okay, and then this is this year, this is today. No active hurricanes in the North Atlantic, no active tropical cyclones, but several areas of interest. And it was funny, they've spent a lot of time talking this year about this was going to be a very active year, record ocean temperatures, and warmest year on record, et cetera. Of course, we all know it's early yet, right? We're just still mid-September, so we have another 60 days of hurricane season left. But there was, I saw in the Washington Post, like on September 9th, right, there was an article about how the meteorologist was concerned that they're going to lose the public faith because there hadn't been as many hurricanes as they talked about. Then the next day, I looked at the National Hurricane Center site like I do most days, and all of a sudden there were four sort of storms developing, right? So since then, we've had a couple of minor tropical cyclones. People in North Carolina who just got 2 feet of rain may not agree, right? But so things are still going on, and there's a lot of a lot of other things that influence when and where storms develop. So take a quick look outside of the tropics, okay? And I'd like to do this because this actually affects good example. We got a good example of this going on right now. What Jennifer Francis and some of the other scientists are really looking at the sort of weather outside the tropics, and the fact that the boundary between the cold polar air and the warmer mid-latitude air is becoming much less pronounced. And that means the jet stream, okay, which is the sort of current of wind in the upper part of the atmosphere that kind of marks off that boundary. So that boundary gets less pronounced. The jet stream gets weaker, so it's moving slower, and it's also more meandering, right? So instead of flowing in a steady current from west to east, it tends to zig and zag, and as it zigs, it brings cold air with it down into areas, further south, closer to the equator, in areas that, might not see it at certain times of year. Let's take this. There's something that just happened here. If you read the news, right? Northern Central Europe, right, just had this tremendous storm. They call it Boris, okay? But in any case, this is a non-tropical cyclone, but it was a result of this very deep, this is the jet stream over Europe, okay? And it marks just this huge dollop of cold air that's made its way down into Europe. And this was actually sort of pushed from the other side of the globe by very, very, very warm temperatures over northern Asia. So the result of that was a sort of jet stream wobbled down that delivered a whole bunch of cold air to Western Europe. Meantime, there was all this heat and humidity over the Mediterranean and the North Atlantic. Remember, a record warm year. So the interaction of those two air masses led to catastrophic flooding kind of in Central Europe. This picture was taken in Czechoslovakia. So these events aren't purely the product of climate change, but they appear to be becoming more and more frequent, okay? And then I'll just sort of wrap up with a discussion. This is has anybody here used 500 millibar maps for voyage planning, things like that? Right. So this is a map of an upper atmosphere weather map, and all sorts of information on here. But one of the things that these maps do essentially is allow you to sort of see the axis of the jet stream. Okay, these little arrows are wind, and we're not at the ground here. We're up at about 18,000 feet roughly, and you can see this current of wind. It's effectively the jet stream, and you can see. So this is today. I downloaded this today, and it's actually a forecast for midnight GMT. So this is actually just about right about now. Okay, and you can see the jet stream is sort of pushing its way, sort of swerving to the south. Okay. Just east of us, okay, over the western North Atlantic. But watch what happens to the jet stream over the next couple of days, okay? So it's today, tomorrow, okay, and middle of the week. And so what we can see has happened to the jet stream is we've got this meander in the jet stream that's kind of pushed its way to the south and actually cut itself off and kind of turned into an eddy, right? So instead of the jet stream, which typically carries most of our weather along with it, instead of a nice consistent stream of west to east wind, it's just this sort of big blob of cold air that's just sort of sitting there and spinning, okay? So in this case, what this leads to is that weather at the surface, instead of kind of developing as warm air interacts with cold air and then kind of moving along, getting carried along by the jet stream, weather at the surface just sort of sits, okay? And Dr. Francis in Woods Hole, she got a very technical term for this. She calls it stuck weather, okay? Very scientific. But let's take a look at we're just going to look at the surface weather maps, okay, for this same interval, okay? So here we are again. This is right about now. We can see we've got a baroclinic, just an extratropical cyclone, or just sort of your standard garden variety low pressure system. This is probably what we'd call a nor'easter, right? Because it's got, we're right now, we're on the north side of the circulation. So we're getting winds out of the east and, quite a bit, right? Offshore, Nantucket Shoal, things like that. They probably have a gale right about now. And they're talking about sort of a fairly wet, windy weekend. But remember what I just said about stuck weather, okay? And watch this system. And also, like typically we would expect these systems to develop and then shoot off to the east. The same with this storm south of Greenland. Okay, and generally you'd expect them to develop and then move pretty briskly off to the east. But watch the weather over the next several days. It's pretty much going nowhere, okay? These systems develop as the jet stream introduces cold air, but because the jet stream has no sort of west to east momentum at this point, these systems, rather than moving, they're just going to be stationary, and in some cases, right, they'll even sort of back up, right? This storm out over the North Atlantic, right? It's actually moving west, okay? Kind of unusual, right? But that's a product of the fact that the jet stream sort of slow and sluggish and creating these captive eddies, okay? So mariners call this, or meteorologists call this, a cutoff low, and a piece of the jet stream sort of severs itself. And again, this happens, right? These aren't purely a product of global warming, but these appear to be becoming more common, right? When, people ask me, right, like a 30-year career of sailing, is there anything you've noticed? As a mariner, usually too tied up in the day-to-day, right, to really think about the long arc, right? But this sort of stuff, I feel like, yes, 30 years, these kind of, not thinking so much about tropical storms, but having spent a lot of time out of the tropic, these sort of stuck things like these, cut-off weather features, very persistent low pressure systems in higher latitudes seem to be more common, right? I'm not a scientist, so didn't have the foresight to collect data across the arc of my whole career. But that's something that observably seems to have changed.
Do we have a surface wind version of this?
These are surface winds. Okay, so we're looking at a surface map here. Okay, so you're looking at the surface counterparts of the jet stream, right? So the first four maps that I showed were upper wind, right? And then we're looking at the behavior of winds at the surface. And so the surface low pressure system is sort of coupled to the jet stream. The jet stream is what they sometimes call like the storm track on weather forecasts, because it sort of pushes low pressure systems. They're kind of like, think about like corks in a stream or something. But if the stream itself is, instead of flowing in a linear way, if it's eddying, right, the cork is just gonna swirl around in a circle, right? So this, this system here, right, this, this is, this is a 96-hour forecast now. So this map is valid on the 22nd. What's the 19th? So this is 3 days from now. And, the weather, so that would be Sunday, right? So the weather on Sunday is going to look a lot like the weather tomorrow and Saturday, right? So we'll be looking at kind of a parked low pressure system here east of New England. Yes, ma'am.
These jet stream issues be impeding the development of tropical cyclones in the southern Atlantic. And I know there's also the issue of sandstorms out in the Sahara.
Yep.
And I remember being in Florida in 2020, really the front of the East Coast really had one hurricane.
Okay.
And we were talking and do the same. Sahara, but I'm wondering about this weather pattern, what impact it's having.
Possibly. I'll just say I don't know. I know they've talked about like one of the things that has been limiting hurricanes. Apparently, they think is perhaps more rain over West Africa. Okay, that's sort of limiting an area where of the atmosphere. It's commonly at this time of the season kind of a breeding ground for hurricanes. But yeah, it's sort of a Rubik's cube to say the least. But what you're saying could be related, right? But I'm not aware of a direct connection. Any other questions?
On that map.
Yeah.
The red arrows. These are showing the direction of the low.
Exactly. Yep.
So two of them are moving south.
Right. Yeah. And so if we, I'll just click back. So this is the forecast for September 22nd, right? So if we look at we go back to the jet stream. Okay. So this is the jet stream forecast for the same time, right? So you can see if you've got a storm that's here, basically it's getting pushed. You think about the jet stream itself is what carries surface cyclones along with it. So, a cyclone that's centered here is actually relatively rare to have easterly winds in the jet stream. But if you do, right, they're going to be pushing, basically pushing the storm back, what we normally think of as backwards, right? We're used to our weather mostly going from west to east. But when you get these eddies, these captive eddies in the jet stream, it will either sort of stall or sometimes even back up. And eventually what will happen is, this will gradually dissipate and the jet stream will reorganize itself.
There to talk about the perfect storm backing up.
You're talking about like the perfect storm.
Big D.
Yeah, the perfect storm. Yep. Yeah, I mean, I don't know what the jet stream was doing at that point, but that was a very powerful, it was just a big, barometric, it was a North Atlantic cyclone, just a big storm, but that also ingested the moisture from the tropical storm, right? That was kind of like not unlike the 2012, right? New York City, right? What was that hurricane? Sandy, right? Yeah. Hurricane Sandy was kind of a similar situation, right? It was a very large, like non-tropical low pressure system that inhaled a cyclone. The hurricane was called Sandy, right? But there was also another very, very active non-tropical system kind of over the northern part of the hemisphere. And all that moisture, all that, warm air and moisture being inhaled by just a normal barometric system, which is like, feeding energy into, it's like feeding fuel into a furnace effectively. Great. Any other questions? Yes, sir.
Well, all this electronically transmitted data, ocean-going ships, would it be possible to update the climate charts with past 5 year data?
Yeah.
It's so much denser.
Yeah.
Boring that.
Yeah. And that's a question I've been trying to get the answer to also. Right? You think if somebody works at a maritime academy, it would be easier, like somebody I could pick up the phone and call, but it's not clear to me what the fate is. Like if you go to the NGA website and download pilot charts, they're 20 years old, right? And so I'm not sure if a current set of pilot charts, like in the traditional format, is being developed or not.
Yeah, the pre-AIS
Oh, yeah, there's all sorts of ways, yeah, to collect data. And there's a lot of data being collected. I mean, worldwide, there's a very robust source. I mean, virtually every merchant vessel is reporting weather data. Yeah. But I'm not sure, I mean, it all goes into like weather models, the prediction system is all fed by data from ships at sea. But I'm not sure about pilot charts, right? I'm not that sort of climatological mapping. I haven't really been able, that's something I've been curious about myself and haven't found the answer to.
I think Jimmy Cornell has got a version of pilot insurance.
Yeah, the sailing atlas.
Yeah,
Yeah.
It's based on recent data from ships.
Yeah, and
Is that true?
he has a version of that. I remember what the product's called. I have a copy of it on the shelf, but yeah, it's like this ocean sailing atlas or something. Right, so that's something he's done on his own.
Right.
Yeah.
I think of Google came out with this.
Okay.
If my memory-
Yeah, I mean, those are a tremendous voyage planning resource, particularly for people traveling on sail. Yeah.
You might be interested to find out how different they are.
Yeah.
18 minutes.
Right, yeah, because certainly the data is denser now. It's interesting, I have an old shipmate, there's a program, there's something called Old Weather, where they're collecting data from historic, like ship's logs primarily, and feeding it into weather models, so you can get things like, if you're looking for like the Galveston hurricane or something like that, they now can put together like a full, like a model run for the Galveston hurricane, so you can get a, like what that data looked like run through a modern dynamic weather model. And it's called Old Weather. You can find it. No, it's an international program, but you need to sit down, you need to give up a few evenings to figure out how to ask it the right question. Astonishing information. Right, well, thank you very much for coming. And I'll stick around if anybody has questions. I do have some books if anybody wants one, no pressure.
We have a
Oh, my gosh.
gift for you.
Swag, thank you.
The pelagic blanket. And,
Okay.
on brand, with the pelagic logo on it.
Oh, thanks so
Thank you
much.
very much for coming
Some
up.
time for blankets even too.